Welcome back to ECE 320A. We're in Unit 8, which is our convolution unit, and we're going to work through a different example in this video. And this video will be to find the output of what happens when we low-pass filter a constant, and we'll do that via convolution. Here's a picture, a block diagram description in the time domain of what we are proposing to do now, and I'm hoping actually that you might already have a feel for what needs to be sketched relative to this question mark underneath. What is the output waveform going to look like if we convolve a constant with this impulse response from a low-pass filter? And this low-pass filter's impulse response will be a first order, and you could think of this as an RC circuit giving you a pole at -2. The DC gain is 1, and we'll talk more about that in subsequent videos. But if the transfer function of our low-pass filter is 2 over s plus 2, then we can inverse Laplace transform that to obtain the impulse response of that low-pass filter, and then the time domain that for non-negative values of time is equal to 2e to the minus 2t. We want to use that as our impulse response for our system, and applying to that system we want to be a constant where that constant actually turns on at time t equal to 0, and it's 4 just as an arbitrary sort of magnitude to give us a way of comparing or contrasting these waveforms x of t and h of t. I'm not going to spend time really on flipping and sliding x of t. Hopefully it's clear that that one might be a little easier to flip and slide. H of t, you can already see, I hope, what that looks like as a waveform. This is a decaying exponential, and the decay rate is influenced by the exponent of -2t. If we then take x of lambda, we flip it across to obtain x of minus lambda. We shift it to the left by this adjustable parameter t, and t again we're allowing to be varied from minus infinity up through plus infinity, and try to find the unique overlap patterns that that waveform x of t minus lambda has with h of lambda. Based on those unique overlap patterns, we can then find the expression for y of t, the output, in certain intervals of time. Our first overlap pattern, or first pattern, is no overlap, and that's when x of t minus lambda, its right-hand side, is not yet up to h of lambda, and this pattern is actually going to occur when, if we look at this, t is less than or equal to 0. And this is our lambda equal to 0 point, and as long as t stays to the left of that, or as long as t is less than or equal to 0, we will have this overlap pattern, which is no overlap between x and h. Since their product would be 0 for all lambda in this particular overlap pattern, then the integrand is 0. We integrate 0 and we get nothing. And for that reason, then we have y of t is equal to 0 for t less than or equal to 0. The second overlap pattern is now when t slides through lambda equal to 0, and now you can see that we do have overlap, and realize that this constant is true for all time after it begins, which means that this blue curve extends off to minus infinity. The red curve is an exponential, and so it likewise continues off to positive infinity. And in fact, this second overlap pattern, I hope you can see, is the final overlap pattern, meaning we only have two overlaps. The first was no overlap, and now we have a second overlap, which is the final overlap. This overlap pattern occurs when t passes to the right of, or is to the right of, lambda equal to 0. And now we can find the value of the expression for the output y of t when this pattern exists. This pattern exists for t greater than or equal to 0. We have the product of the x of t minus lambda, which has a functional value of 4, times the functional value of our impulse response of the low-pass filter, which is 2e to the minus 2 lambda. And this is now going to be integrated from the low end of our overlap interval, which is lambda equal to 0, up to the value of this variable t in our overlap picture. So now we're going from lambda equal to 0 up to lambda equal to t, and we can now integrate this. We now have 4, and we have the 2 if we bring that through, and then the minus 2 from the exponent. We have e to the minus 2 lambda, and that's now evaluated from 0 to t. The 2's cancel. We have minus 4 evaluated at e to the minus 2t, or the upper limit, minus e to the minus 2 times the lower limit, pushing the negative sign through and basically changing or distributing the minus sign into the square bracket, which I'm going to now create. I have 1, which this particular expression goes to 1, and then we subtract from that e to the minus 2t, and that's true for t greater than or equal to 0. That's now our y of t expression, and remember, y of t was nothing for t less than 0, and it's 4 times 1 minus e to the minus 2t for t greater than or equal to 0. Or pictorially now, and that's what I had suggested you might already be seeing in your mind mentally at the output of that block diagram, we have put in or injected an input that's constant that turns on at time 0. This is now our x of t. Maybe I should have labeled that closer to the t equals 0 origin. So let's say this is now x of t. And now y of t has this buildup at time 0. We don't have anything. We have 1 minus 1 in the square bracket. But after that, now we have a time constant that can be found by letting t equal tau when that exponent is equal to 1, or tau is now 1/2. So after 5 of those, we should be basically at our final value, or at 2.5 units of time. If I can sketch this, now we would have for our output something like that for this low-pass filtered constant. And we should, I think, have anticipated that based on what we have already seen when we low-pass filtered a pulse. Now we basically never turn that constant off, and we should just see this exponential increase. The exponential rate of increase will obviously be influenced by the dynamics of the low-pass filter, which is given to us from the low-pass filter's impulse response, which is this e to the minus 2t. If we had a wider bandwidth or a larger bandwidth for our low-pass filter, this exponential increase would actually be sharper, and we would start to see something that's even closer to the constant x of t in the output y of t. But that's now what happens when we low-pass filter a constant And that should be consistent with your intuition and your ideas about what we would have expected.